tonight. But as I sit here tonight in Maryland and I look up at the sky, we have some amazingly menacing looking cumulonimbus clouds. We're probably going to have a little bit of thunder and lightning. And we certainly have had storms since, since I was a kid. I'll always enjoyed the energy and the power of them. But I know that we have seen increased precipitation as a result of many of these summer thunderstorms that we're having. So many of us are just experiencing changes in the weather patterns as we experience them in the different places that we live. So tonight we're going to be doing a deep dive into that and hearing from some of our leading scientists about what they're learning, getting some ideas of some places that we can go and gather more information. And so let me tell you a little bit about our guest speakers tonight. You can get their full bios on the webpage that you registered on. And I'll also put that in our chat in a little bit. So we're going to be beginning with Dr. Bob Adler, and he is a senior research scientist since 2018 in the Earth Science System Interdisciplinary Center at the University of Maryland, College Park. He had a 35-year career at NASA Goddard and is a distinguished alumni of the Colorado State University Atmospheric Science Department, as well as a fellow of the American Meteorological Society. Bob has received the NASA Goddard William Norberg Award for Earth Science, the NASA Outstanding Leadership Medal, and the NASA Exceptional Scientific Achievement Medal. Dr. Adler's research focuses on an analysis of precipitation observations from space on global and regional scales. Then we're going to hear from Dr. Andrey Savtchenko. He joined NASA Goddard Space Flight Center in the year 2000, supporting Earth observing systems. He's been involved in providing science data analysis while supporting numerous missions, too numerous to go through them all right now, but they include the Tropical Rainfall Measurement Mission and the Global Precipitation Measurement Mission. Then we have Dr. Robert Emberson, who serves as the Associate Program Manager of the NASA Disasters Program. He has supported the Disasters Program since 2018 as a center coordinator, providing satellite data and insight to a range of stakeholders before, during, and after disaster strike. Emerson is excited to leverage NASA's unique assets and knowledge to improve the resilience of communities around the world from hazards and disasters. And then we're going to have Jacob Reed, who has been a close friend and colleague since 2011 when I came on and joined the Global Precipitation Measurement Team. And he is the digital outreach lead for NASA's Disasters Program and for the GPM, Global Precipitation Measurement Mission. In his 13 years at NASA, Jacob has built and managed multiple websites, including the GPM website and our precipitation our precipitation education website, which you're going to see many resources on when you look at our resource packet. And he has written and edited several science articles and developed many outreach materials to help dedicate and inspire people all over the world. So without further ado, let me go ahead and welcome Dr. Bob Adler to go ahead and give us our introduction to extreme weather. And I'm going to stay on here, Bob, until I let you know that I see your slides and we're looking good.
How are we doing?
You're looking perfect. I see them beautifully. And folks, as Dr. Adler's presenting, you're welcome to have questions that relate to what he's talking about in the chat, and then he will respond to them after his talk. All right, Bob, I'm going to disappear here and let you go.
Okay, well, hello, everyone. Well, let's talk about extreme weather. What are we talking about? Well, like I have a list here: hurricanes, thunderstorms, tornadoes, snowstorms, dust storms, floods, landslides, and even drought. And I'm kind of leaving out heat waves and cold waves. But one of the key things here is almost all these extreme weathers are associated with precipitation. And why the heck is that? Well, the answer actually, in a very general sense, is that the energy related to the phase change in the atmosphere from water vapor to liquid and frozen water essentially supercharges what might be mild circulations and can make them extreme. Like the guy holding the very large hailstone in the picture there. I'm not allowed, I can't advance my slides.
Well, that's not a good thing. All right, let's see here if we can figure out why. And if not, I'll go ahead and I will put your slides up on my.
I've got it.
All
I've
right.
got it.
You got
Okay. So must have been something I was doing. So precipitation extremes. Well, again, flood, landslides, but also we're talking about climate monitoring here tonight, and satellites. Well, what kind of satellites? Well, like the US-Japan Global Precipitation Measurement GPM mission, which is sponsoring this webinar. And of course, one of the things we're interested in are things changing on our planet? And if so, how? And here's a dirty little secret I'm going to come back to and further in the talk. The temperature of the planet is unnaturally warming due to the results of our civilization. But the total global mean precipitation is staying about constant. And that's not good. And we'll figure out why that's the case. And talking about GPM, it's actually a whole set of satellites. There's one core satellite, oddly called the GPM core, with the radar and passive microwave instruments, and a constellation of about 8 research and operational polar orbiting satellites, also with microwave sensors that provide the data for real-time analysis and produce pictures like you're seeing in the image there. And we use the satellites in a way, using the core satellite to calibrate or adjust the other satellites, and then do a little space-time integration and some other tricks, and come up with images like you're seeing on the screen at about 10-kilometer resolution and 30-minute resolution all over the globe. And that product is called iMerge. And it's very valuable both in a research setting, but also for real time. And one of the things that we do in my group is we developed a global flood monitoring system. You can see the website there, although it's not quite working at the moment. But essentially we start, and I hope you can see my cursor, you start with the GPM iMerge product and take that rainfall, put it into different models, land surface models to get the runoff, put it into routing models that take the water that's left over on the land and put it into streams based on elevation maps. And then you're able to finally get stream flow as a function of time. And you can see it increasing in the figure in the bottom right here. And then based on previous calculations over a number of years, you have an idea of what the flood threshold is at each point on the globe, over land, obviously. And you know when you're above that. And the next thing you can do is actually produce or calculate an inundation map. And you can do this at fairly fine scale resolution at 1 kilometer. So the thing to keep in mind is you can go from precipitation, that 30-minute, 10-kilometer data set that GPM is giving you, and you can come out with inundation mapping. Now let's take a look at one example from a couple of years ago, and this was a paper that you can reference if you want to. But in Mozambique, Cyclone Idai, back in 1919, it was very devastating. There were 1,000 deaths, 100,000 homes destroyed, and you can see a picture here of what it looked like over a fairly wide swath. And we're going to come back and look at this inundation map that was produced. But first we'll look at the rainfall. And this is a 7-day map of the rainfall, total rainfall produced from that iMerge product, that GPM product. And you can see the swath of the storm as it came from the the Indian Ocean onto Mozambique. and it created the havoc. And the maximum rainfall you can see in the map here, there's a 300 millimeter is the red area. But in the middle of that, there was actually a peak of 600 millimeters. And that is about 20 inches or more. And when you have that much rainfall, obviously something is going to happen. And when you look at a map at a particular time of day here, you can see a map of this where the stream flow was above the flood threshold. And you can see the tremendous amount of area here that was covered by the flooding. And if you look at a specific point over here and look at the time history at that point, you can see the stream flow starting off near zero and then coming up over the threshold and going way high compared to that flood threshold, and then decreasing with time after the flood passed. And actually, our calculations may have dropped that stream flow too fast as compared to what was happening actually. But then the final thing is, and the thing you're interested in is, where exactly is the flooding? And if you can produce a flood inundation map, it's a calculation based on the rainfall and all those models. But this is what you get coming out of our system. And essentially, you can think of this as a final result from the iMerge product. And the dark blue areas in here, we also calculate the water depth above the flood. And that's actually a meter depth here, which is a very large depth when you're dealing with a wide area like this. Now, we like to validate these things. You oftentimes can't do it right away. But here's a image from the synthetic aperture radar that passed over about between 7 and 10 days later. It's actually a composite of different overpasses. And you can see in general that we're getting the flooding in the right areas. So having this kind of information at an early stage during an event can be very helpful for people trying to decide how to help the people on the ground. But let's jump back now from a particular flood case and talk about precipitation averaged over the entire globe. And as I mentioned before, if you look at this, even though there are variations and our time history goes from, in this chart, from 1979 up to the present, or at least through 2023, you can see even though there's fairly large variations, and I'll come back, they're not really that large, but the total global precipitation is just about constant, even though the global surface temperature has been going up very rapidly. Now, the variations you're seeing here are actually pretty small. The range of values is only about 3%. The global mean rainfall or precipitation is about 2.7 millimeters per day. So we're not talking about a lot here, but you can obviously make out these variations. And here we're going to start talking about ENSO, or El Niño's, the Southern Oscillation. And you can see the peaks in the global rainfall. This is annual average rainfall over the entire planet. When you're in an El Nino, as indicated by these E's, you're at a high point. And when you're at an L, La Nina, you're at a low point. And there's another low point back here. And that's when we had a volcano affecting the circulation, affecting the amount of sun that was reaching the surface of the ocean and reducing evaporation. And that also produced a very low global precipitation. Now, when we talk about El Nino, it produces tremendous variations in precipitation across the globe. And the map you're looking at right now are anomalies in precipitation for all the El Nino months, all composited together during this close to 40-year period. And what you can see immediately when there's an El Nino, which has very high surface temperatures over the ocean in the Central Pacific, over that area, you get a tremendous surplus of rainfall. That's the green areas are the plus, as you can see down here. But because you get tremendous upward motion over that area, that air has to come down somewhere, and it comes down in different places. For example, to the west of there, over the maritime continent and even Australia, and that produces a rainfall deficit over these areas, a rainfall surplus over the Indian Ocean, a negative anomaly or a rainfall deficit over South Africa, Northeast South America, and of course a rainfall surplus during El Nino across the southern United States. And you can see some of these features extend to fairly high latitudes, even touching Antarctica. In the next slide, I repeat the El Nino map of the anomalies in the top panel. And in the bottom panel is the La Nina composite, all the months where La Nina conditions were evident in the Central Pacific based on sea surface temperature. And if you look at these two things, it doesn't take much to say, whoa, these two maps are essentially a mirror image of each other. And that's exactly correct. So you can see in the Central Pacific where you go in El Nino from a tremendous surplus of precipitation. Now the brown area is indicating a very large negative anomaly, a lack of precipitation. While over the maritime continent in Australia, now in La Nina, you have a surplus of precipitation. And what typically happens, for example, in Australia, which you can see the entire country or continent is covered here, when you're in a La Nina, they tend to have floods. When you're in an El Nino, they tend to have a drought and fires. So here's where you get the extreme conditions, and you can see these kind of things happening even on global maps. But let's talk about trends in global temperature and precipitation. On the left panel is the map of how temperatures are changing. And where you see all the red, which is essentially covering most of the map, that's where you have a positive trend. You can see the scale down here. And there's only very small areas during this period where you actually have a negative temperature, although you do have a negative temperature trend, although you do see a little bit. But essentially, the planet is warming almost all over. If you look at the precipitation trend map, you get a very different picture. You have areas of precipitation increase over the period, as indicated, for example, in the blues, and precipitation decreases, for example, the browns and the reds. And if you squint a little bit, you could say, you know, if you sum or average over that entire map, you might come out with near zero. And that was that time plot that I showed you before, which shows that even though the surface temperature is going up, the mean precipitation across the planet is staying about the same, but things are changing in different places. And we're tending to get a wet getting wetter, dry getting drier. That is, areas that tend to be wet are now seeing more rainfall or precipitation, and areas that tend to be dry are getting less precipitation. Now, that's not true everywhere, but that is a general phenomenon. But even more importantly than that is that there are trends in intensity of precipitation. And here we're looking at a very large scale, tropics 30 north to 30 south, just the tropics, land and ocean combined at 2.5 degrees in monthly. And on an annual basis, we're picking out very heavy rain areas, the 95th percentile at that grid spacing and time scale, okay? And the observations, which are shown in black, and they're from the Global Precipitation Climatology Project, which is a combination of satellite data over both ocean and land, also combined with gauge information over land. And as you can see on the heavy rain end, the 95th percentile, you can see there's a trend upward, even though you can see some variations. And actually, some of those are related to ENSO. When you go to a lower percentile, you can see a decrease. See the black curves decreasing here? And that means kind of that the dry areas are getting drier, or the dry areas are expanding. Now, this is kind of serious. The other colored curves here are from climate models. And as you can see, they get the same sense and direction that the observations get. That here in the 95th percentile, they're showing, the red and blue curves are showing an increase with time. And the 30th percentile, the drier areas are showing a decrease in that rain rate at time. But one of the scary things, and really the bad news about this, is that when we compare the rate of change of the observations, the GPCP data, at the 95th percentile, and we subtract the mean values off of there to keep it steady, you can see that compared to the models, which are labeled here as AMIP and CMIP, we get a larger magnitude of the trend. And that's true actually on the dry end of things over here. So unfortunately, the observations may be showing a faster intensity change than the climate models. And that's not good news. So what does this all mean? Well, extreme weather is nearly always driven, or maybe I like to use the term supercharged, by precipitation. Satellite precipitation information is important to analyze the extremes and their impacts. I gave the example of floods. We'll hear some more about other things, but also to monitor and understand climate change. The global temperature is increasing, but the mean precipitation is about constant, but it's changing its form. Things are moving around. El Nino and La Nina are there. And also we see the wet getting wetter and dry getting drier. Now, the ENSO, or El Nino La Nina phenomenon, was here before climate change, and it seems to be continuing to occur with climate change. But the next point down here is maybe the most important. The intensity is changing. Even at a large scale, intense rain is increasing and dry areas expanding. And what these climatic changes can only lead to are more wet-dry extremes and more floods and droughts. And I'll stop there, and I hope I've made things clear for you. Thank you.
Dr. Adler, that was really an amazing overview for having 15, 20 minutes to just kind of give us the basics. And I put in a couple of links related to what we call the ENSO patterns, the El Nino, the La Nina. They're the kinds of things that every now and then we've heard about in school and then we kind of forget. So I'll let Bob give a little more information in the chat window and tell you a little more about that. And next we're going to hear from Dr. Savtchenko, and he's going to give us a better understanding of how climate change is impacting these extreme events that we're having. So thank you again, Dr. Adler, and I know he will continue to answer questions in the chat box. And thank you for having these questions about the topics, and keep them coming. All right, without further ado, and let's see, Bob, we need you to stop sharing, although maybe Andrey, you can go ahead and start. I can't quite tell.
Yeah, hello everyone. I'm Andrey Savtchenko. Hello from NASA Goddard Space Flight Center. I'm at work here. It's 8:30 in the evening, but still, it's my pleasure being with you. So I will stop my video just to spare some bandwidth, and I will try to share my screen.
I will let you know once we see it, Andrey, so no worries. I'm keeping an eye.
So that should lead you to my, I hope it's,
I'm not seeing it yet, but
not yet.
not yet, but sometimes it can take a little while.
Let me try again. Try to this, share.
There is no perfect system, as we have found, but this Zoom system seems to be better than most. So we shall hope that that it all works out.
Okay, let me try another thing.
Of course,
Let me try another thing.
I just chatter to let you know I haven't disappeared. I hate it when sometimes you're just talking into the Ethernet and you're not even sure if people are still there. So keeping an eye out here. Yeah, the impact of climate change on these extreme events. I did a lot of research on this, and so you'll see when you take a look at that resource packet that you're going to find a lot of resources related to that. And this is a real fascinating, area of research, and one that certainly having the satellite data is helping. We're looking great, Andrey. We just
finally, yeah, sorry for that.
It's all good.
Guys, slideshow
Yeah,
still there?
you're good. You're perfect. You go. Drum roll.
And if I can turn my laser pointer, that will be the
Hey.
top of it.
And then
Okay.
we're good.
All right, sorry for that, folks. So that's the topic of my presentation. Very loaded topic, impact of climate change on extreme precipitation. Can hardly cover it in 10 minutes, of course, but I will try. Bob did, of course, most of my job, most of what I wanted to present. So my job is much, much easier. I will start with a cartoon that I love. It's from a very nice paper by Kevin Trendberth. And it shows the global mean energy balance. And what is important in this cartoon is to know that evaporation and precipitation is part of the Earth cooling system. Together with the infrared radiation, these two are the major components of the Earth cooling system. And they're very finely tuned. There is very fine balance between the two. So you cannot change evaporation by much without changing the infrared cooling and vice versa. So these two are very finely tuning. One cannot change a lot without impacting the other. That's why early on, people started thinking that very likely with the warming climate, the mean precipitation, again, the emphasis on the mean precipitation, probably will not change by much, what we saw from Bob's presentation, but the regime, the character of precipitation probably will change. Probably we'll see longer dry periods followed by short bursts of heavy precipitation. And indeed, if you look at the Intergovernmental Panel on Climate Change, I have the URL down here. That's the most recent assessment from 2022. And this assessment is probably the most comprehensive assessment of the current knowledge we have of the climate change. Very nice complication of enormous volume of work. So what the IPCC is saying that recently there is more and more robust evidence that mean precipitation, again, the mean precipitation will be changing at slower rates than the water vapor, which is the thermodynamics of the climate change. And also the water cycle, what the cartoon is shown here on the right. The water cycle is, there are evidences that it will intensify and not accelerate what's the difference between intensification and acceleration? Sounds like the same thing, but it's not. The acceleration would mean, look, for example, at this branch of the water cycle of the land. This is the land precipitation. This means this cycle will not accelerate. It may be even slow, so that the precipitation events probably will be even will have more rare, but what will happen, this precipitation will intensify, like Bob emphasized. When it rains, it pours, and when it's dry, it's really dry. So that's from IPCC. Furthermore, in the IPCC, you can see results from simulations, and this another cartoon from IPCC. And just let's look at the most left here at so this is different scenarios. What will be happening again with the mean precipitation? What change, how much mean precipitation will change at different warming scenarios? And it's 1.5 global warming. This is probably, we're striving to be within that. If you remember the Paris Agreement, this is what we want to be. So this is the scenario where we strive to be as a civilization. So at a simulated change at 1.5 degrees Celsius warming, so the change in the mean precipitation is in very small amounts. So for example, if you look at like North America, part of it, there will be even drying. Some mean precipitation will be drier, and a big part of the North America actually will be between 0 and 10% change for the 1.5 degree Celsius change. And by the way, 1.5 degrees change, it will be like for about a century. So by mid 21st century, we probably will hit that 1.5 degrees warming as compared to the pre-industrial period. So very, very small change. It's next to impossible to get it with the observations that are still very short. And so that was simulations. These are, and this is again from IPCC, but these are observations. On the left, you have observation from rain gauge, probably one of the most accurate you can find, and longest one. So this is almost 100 years. It's from, it is actually 83 years. It's a rain gauge observation. And this is, these both panels shows trend in increase of mean precipitation. So this is rain gauge, and this data set actually was authored by our esteemed first presenter, Bob Adler. This is a GPCP, very nice data set, very nice, very suitable for climate studies. And like Bob said, you see there are, it's not a very coherent picture of increase, decrease, of increasing or decreasing trends of precipitation. But the important thing, note this axis. Axes are like everywhere over land, especially over land where we care. And axis means non-significant trends, or in other words, we are not very certain. There is low confidence in these trends from the rain gauges and from the observation. This is fused satellite observations, 30 years. So why? So can we have an example of that? Can we go look at sign of this thing, like big excursions of precipitation? And one place to go to is California, and the reason is not in the last place is that California is just one state in the United States, but California is the fifth largest producer of agricultural products. Fifth in the world, not in the United States, in the world. So it's interesting to go to California to see what's happening with precipitation there. And look at this. So this is Lake Oroville. This is Bidwell Bar Bridge this year. It looks pretty nice, isn't it? It's very nice. It's a picture from May this year, taken by California Department of Water Resources, who is managing Lake Oroville. So this is May this year. Just 2 years ago, the same bridge, it's almost no water. So the September 2021, this is the beginning of the water season in California. So just in 2 years, from almost empty to now Lake Oroville is 90% full. Another bridge in Lake Oroville, this Enterprise Bridge, it's again picture from this year, from April 2024. This year looks very nice. And just 2 years ago, this is the end of the water season in California in 2022. A very, very dry picture. So big excursions from very empty to very full. So that's obviously you have to be a very good water manager to manage situation like that. So it looks good, right? So that's full. Lake Oroville looks full. Very comfortable picture. But if we take GPM data and we calculate how much actually was accumulated, how much precipitation was accumulated this year, we see that actually California as a whole was 8th driest year. So don't be fooled by some pictures where showing full reservoirs. California as a whole was 8th driest year. That's what GPM is telling us. And on this slide, I'm showing accumulation of precipitation for every year since we have the GPM data and TRIM data. So this is iMerge. We have iMerge since 2000. So this accumulation of precipitation for every year since 2000. And these are years ranked from driest to wettest. And notice that thing, just in 3 years, in 2013 was the driest year in California. And 3 years later, that is the wettest year in California, 2016. That's the beginning of a pretty famous water season in California, 2016. In February 2017, there was a big incident in the same Lake Oroville. There was the emergency water spill. Water spill suffered damage, and there was a big scare in this water season. About 100,000 people were evacuated because people were scared that the dam will not hold. Oroville Dam is very interesting. It's an earth-filled dam. It's the highest, it's the tallest dam in the United States at about 760 feet. So why is that? The Lake Oroville looks full, but it's an 8th driest year. So how is that possible? Again, let's look at iMerge data. And here I'm showing the accumulation of precipitation is related to the expected season. So this season started somewhere in August, September last year, lasting till May, and this is related to the expected season. So what do we see? We see that actually most of the precipitation, about 2 times the seasonal expectation, was in a narrow strip in South California around the coast, Los Angeles, San Diego, Tijuana, here's Santa Barbara. So these are the places, some of the places got about 2 times seasonal, but how about the rest? Here we are dry. Practically north from San Francisco, half of California, the entire north is on a dry side. And here is Lake Oroville. It is pretty much normal. So here is the Lake Oroville. Probably lucky, probably collecting water from this watershed similar here from the west. So, okay, so we see here that this is where the most precipitation fell. How did it fell? Was it like some moderate? And probably not. Looking at this next slide. This next slide shows accumulated precipitation in just 6 days. This is in February 1st to February 6th, this is when a couple of atmospheric rivers made landfall in California. So how much precipitation fell related to seasonal? Look at this. This is for just about, and it wasn't raining all these 6 days as atmospheric rivers were hitting California here in the south. It was raining for about 72 hours, but what happened? For 72 hours, these areas collected more than half the seasonal. For 72 hours, more than half the season. So this is relatively dry places, very unexpected for them. Of course, the drainage systems in Los Angeles, San Diego couldn't handle that intensive precipitation. And this is my take-home message. My last slide. So it's time and again, as Bob said, and I will repeat that it's very likely what will be happening with warming climate. It will be intensification. And remember, what's the difference with acceleration? It will not be more frequent precipitation. When it rains, it very likely it will be poor, and when it's dry, it's really dry. And this is all from IPCC. So this is compilation from the brightest mind in climate change. And also, my last bullet is there is high confidence. There is high confidence that very wet or dry season and weather patterns will intensify in a warming climate, such that wet spell will become wetter and dry spells drier. Just to reiterate what Bob Adler said. And back to you.
Thank you so much. You certainly have given us a whole lot to chew on, a whole lot to think about. And when you do look at that resource packet that I made up, Andrey had been kind enough to send me the specifics from the IPCC 6th report, which is the most recent. So you will find that in the resource packet, as well as a video that was pulled together that talks about the impact of climate change on the water cycle. So next, we're going to do a deep dive into one of these types of disasters, and we're going to be looking at landslides. So we'll hear from Dr. Robert Emberson to tell us a little bit about landslides.
Thank you, Dorian, and thank you so much to everyone for joining tonight. I'm really excited to present some of the work on behalf of, I'm sorry, this is actually the wrong part. I'm going to stop showing that one and share the right window.
Yeah, let you know when we see it perfectly, so you're just fine.
So I'll get this right in a second. One moment. I'll do it this way around, shall we? And we'll go that way. Okay, hopefully you can see my slides.
Perfect, yep.
Perfect, thank you so much. So my name is Dr. Robert Emberson. I'm part of the Goddard Space Flight Center Landslides research team. And you may be thinking, well, why are landslides part of this presentation? We're talking about GPM and we're talking about rainfall. Well, GPM, here I'm showing a visual of rainfall patterns around the world. This is pulled from the NASA's IMerge dataset, which Dr. Adler so effectively explained. Rainfall is critical around the world, not just in terms of setting patterns of drought and extreme rainfall, but it also drives a number of other types of hazards, and landslides are one of those that we think about extensively. Rainfall is involved in flooding, it is involved in hurricanes, but it builds hazards, a kind of a compounding effect of extreme rainfall. And the landslides research team at Goddard has built upon decades of research into the GPM systems and rainfall around the world to understand more about where landslides are happening and how that can be, how it can inform disaster response. And I just want to talk a little bit about some of those results today. So a most stark example would be to look at a hurricane. We know that during major hurricane events, and here I'm showing some the precipitation using IMerge rainfall data during Hurricane Eta. This is now a couple of years ago. This is 2020. Hurricane Eta impacted Honduras, Nicaragua, Guatemala, and Belize with extreme amounts of rainfall over several days. And in fact, this was a compound event in that there was a hurricane that followed several days after called Iota. And this was one of the most severe disasters to have occurred in Central America in many, many years. The result was extensive flooding, but also extensive landsliding. Central America is a very steep part of the world. And we know that that's triggered by rainfall. As rain falls on steep slopes, the soils become saturated with water, they become heavier, but internally to those hill slopes as well, the friction within those hill slopes is reduced because the water essentially starts to like decouple some of the I guess the connections between soil granules, and it means that landsliding and slipping and sliding of material becomes much more likely. So we know that there is a strong relationship with extreme rainfall and landslides, and in this case we saw it play out. So I'm just going to show a couple of images here. This is a before and after image from after Hurricane Eta, this event in Central America. On the left-hand side, this is a true color image. This is what we've seen in the area, sort of in the mountainous areas of Nicaragua. We saw that there was, essentially forested hill slopes and some towns in parts of this area. On the right-hand side, we're seeing the same area, but this is an image now colored red, is coloring vegetation. This is a false color image used by landslide scientists to isolate locations where landslides are most likely. And what we've also drawn is polygons, these like green shapes around where landslides have occurred. And what you'll begin to realize is that this is not just one landslide happening in a small area. This is tens, hundreds, maybe even thousands of landslides across areas like this snapshot. And this is something we see play out not just in this setting, but also around the world, that when we have extreme rainfall across large mountain belts, particularly as a result of hurricanes, we can see landslides that could be thousands or even tens of thousands. We have recently seen rainfall in Brazil that created, our team was, the landslides research team was involved in mapping over 4,000 landslides in this setting. So there's huge amounts of this. And even though landslides can happen in places that aren't necessarily populated, in these like sparsely populated hill slopes, they can still, one landslide is all it takes to crush a house or to cut off a road, which can lead to community isolation. And so the impact of these can be felt even by one single landslide. So we have to think a lot about how we can start predicting the potential for landslides in areas like this as a result of extreme rainfall. So one thing that the research team at NASA Goddard Space Flight Center has developed over years, as I said, last several years, is landslide susceptibility analysis. So we know that rainfall is the often proximal trigger for landsliding. It creates the conditions that lead to this short-term collapse of hill slopes. But the long-term parameters that might create the risk of landslides can be pronounced, can form over long periods. And these are things like the slope of an area. So steep slopes obviously are more likely to fail than shallow slopes. Slopes that are forested tend to be less likely because trees have an effect of binding hill slopes together. The roots effectively bind hill slopes. So deforestation can create increased risk of landslides, increased susceptibility to landslides, And a few other factors go into this. And so the team has developed global landslide susceptibility maps that use a lot of these long-term parameters to estimate where in the world it's most likely for landslides to occur. And you can see, as you might be unsurprised to learn, mountain belts in the Himalayas, the Andes, the Rockies, and the Alps tend to be the places where we see this the most high potential susceptibility to landslides. But there are other parts of the world where this is important too that you might not think about. Certainly parts of Africa where in the Rift Valley landslides can be important. And also in parts of, obviously Japan have very high landslide potential, and in certain parts of southern Brazil as well. So there's lots of parts of the world that we think about and pay attention to when landslides are happening. So we have that susceptibility model. This exists now and has been produced by our team for several years. How do we go from that to thinking about a real-time assessment of where landslides could happen? Well, our team has developed a system called Lassa, named after the city in Tibet, but it stands for the Landslide Hazard Assessment for Situational Awareness. And what this is it uses the static factors that we use to define susceptibility, and it adds to that this satellite rainfall data that we've talked about already today, this eye-mode rainfall data, as well as soil moisture to understand more about the kind of conditions that might be potential triggers for landslides. We also have a component that includes potential earthquake triggering for landslides, so we think about that. And what that gives us is a landslide nowcast, and this is something that we refer to as a nowcast in that it's something that says every 3 hours we give a probability in every grid cell around the world of potential for rainfall triggered landslides, as well as post-fire debris flows. And that's something I would love to talk more about, but if you have questions, I'm happy to answer, but it's a bit more extensive to discuss than we have time for today. But that rainfall triggered landslide nowcast tells us something about the probability within a single grid cell of a landslide occurring. And we can add to that a population exposure model. And by that, I mean, we can think about where people live, where the infrastructure that they use is, so where the roads are, where the schools are, where the fuel stations are, where the critical power infrastructure are, and think about the overlapping potential for hazard and thinking about where the people and infrastructure is, and that gives us a sense of exposure to landslides. So what does this look like? I'm actually going to use now an example from Central America during this event as a result of this rainfall from Hurricane Eta. We're looking here at a map of, as I say, Central America. This is now kind of central Honduras and Belize and Nicaragua. And the bright colors, the intense warm colors, show the potential for landslide hazard. So this is what we produce every 3 hours. It's an estimate of the potential for landslide hazard in every given grid cell. You can also see overlaid here is the road networks, and this is pulled from a number of different data sources, but essentially this is showing the potential, the large highways, the primary roads in this part of the world. And you can see there are certain areas where the landslide potential is very high in areas where there is also critical road infrastructure. And certainly there are areas where single roads impacted by landslides might lead to entire communities or entire parts of a country cut off for long periods, which can lead to important considerations for disaster response. So does this work, I guess, is an important question to us to answer. So in this example, yes, in several of the locations where we predicted high landslide potential, we then went back to look at the satellite, the high resolution optical satellite imagery, and we found that there were extensive numbers of landslides in several locations, including these 2 boxed areas from this day. From other potential locations that were highlighted in other days of this event, we also found high areas of landslides. So it's been tested several times around the world in multiple different settings, and we found that this is performing pretty robustly. There are false positives, of course, because we tend to err on the side of caution. But we're beginning to build a picture around the world of where landslides are most likely, and every single day, we can give a sense of the people who might be exposed to those landslides. And this has allowed us over long periods to build an estimate of exposure to landslides around the world of people and infrastructure. And so what you're seeing here is a map globally of the potential exposure to landslide hazards over the course of a given year. And the units here is essentially people exposed to a nowcast per pixel. And so you can see in some places we have typically only 1 or 2 people exposed to landslides, a single landslide hazard in any given year. But there are lots of parts of the world, again, in these places where we've seen high susceptibility, that we do see potential for exposure. The interesting thing is that this isn't just the same as looking at susceptibility. We now are building a population map, and we can see that places like Central America, whether it's densely populated, certainly India, where there's a lot of densely populated areas, and Africa have potential for very high landslide exposure. And this is something we can contribute to planning for communities. And why this matters is when we start thinking about reports of where landslides have impacted people. So the graph, the figure on the top here, is a map of estimated loss of GDP as a result of landslides. And what this means, essentially, I mean, you're seeing that there's parts of Colombia and Central America, but a lot of places in Europe and Japan where there's extensive estimates of GDP loss. Now, the reason this is different from our estimate of exposure is because this GDP estimate draws from reports about landslides. Now, typically reporting on landslides is limited to countries where there is good resources to do that. And typically that means developed countries and countries that have long-term infrastructure to maintain these kind of long reporting of losses as a result of landslides. So you can see that developed countries like Italy, Greece, and Japan, and parts of Colombia as well, typically show these high GDP losses, but the entire continent of Africa is missing any estimate of potential loss due to landslides. But when we use satellites to assess a more consistent global model of potential exposure to landslides, now we see that there is a significantly higher exposure in these parts of the world where maybe there isn't the reporting capacity, but we can build a much more consistent picture, and it allows us to make a much more kind of well-defined and comparable picture for the entire world. And we think this is a way that satellites can ensure equality across different parts of the world, and consistent access to data allows us to make informed decisions about disaster response. One of the other real benefits of this, and this is just, I guess, a nice example of how NASA works with groups both internationally and globally, but also very locally, we've worked with the city government of Rio de Janeiro to develop a landslide hazard assessment and exposure assessment tool that's based entirely on this Lassa model system. So in other words, it's using the same tools and same information, but ultimately it's built using very specific data from the city of Rio de Janeiro for the infrastructure and for the population data. And this means that they can isolate specific roads and districts of the city that have potential for landslides. And they found this has been very successful in helping define hazard in the city. And this is to the extent that in Rio, they have partnered with some navigation apps for driving. So this will be your GPS on your dashboard. And landslide hazard warnings about certain road segments will be issued to drivers who are driving through some of these areas as a result of this kind of partnership with the Waze app in this setting. And we think this is a really effective way of getting NASA data, not just from communities that need this, but from satellites all the way down. By developing methods that can be applied locally, we can get that all the way down to people who are benefiting on the ground and making day-to-day decisions in their lives. So we really like this example, and I think it's a good example of how rainfall data can be used for these really dynamic applications. So thank you so much. I'd be happy to answer any questions. And again, thank you for your time.
Thank you so much, Dr. Emberson. Really, really appreciate it. And I did see a question or two for you in the chat, so if you'll take a look at that. And, it's impossible in 10 minutes to really give a complete picture. So please do look at our resource packet. And there I did a deep dive into some of the amazing work that's being done by Dr. Emberson and plenty of other folks who are working with the satellite data as well as, real-time ground data to be able to predict, monitor, and respond to these disasters. So we're going to finish up tonight with my dearest Jacob Reed, who works with the NASA Disasters Program, and he's going to give us a feel for how we respond during disasters. We're going to go a little bit past 9 o'clock. Do not feel rushed at all, Jacob. If any of you can't stay past, don't worry, because we're recording this, and it will be included in our resource packet sometime tomorrow. So carry on, Jacob. I'll let you know when I see everything just fine for your PowerPoint.
All right, yeah. Let's see. So, how does that look?
Great. Thank you so much.
Great. So yeah, my name's Jacob Reed. I'm in communications with NASA's Disasters Program, the digital outreach lead. So I handle web and social media and events like this. So what is NASA's Disasters Program? To understand that, you really have to understand how we view disasters and what a disaster is. So we like to say there's nothing natural about disasters. And what we mean by that is that a disaster is more than just the hazard. A disaster only occurs when a hazard actually impacts a community. And so the choices that we make as a society can actually mitigate disaster impacts. And by building a better understanding of the hazard, the exposure, and the vulnerability of those communities, then we can help decision makers to protect lives and livelihoods. And another a great anecdote I like to use to distinguish between what a hazard is and what a disaster is so if you think of a hurricane, that's out in the ocean, it could be like a super powerful Category 5 hurricane, but if it never actually hits a city or a populated area, then it just remains a hazard. But once it impacts, a coastal area or a city and causes flooding or storm surge or wind damage, and that's when it becomes a disaster. And so that's what we're interested in. And so we take sort of a holistic approach to looking at, the community's exposure and vulnerability, the resources they have to the infrastructure and the, recovery resources that has a huge impact on how a disaster can affect a community and how quickly they can recover. So in order to address disasters, the Disasters Program has 3 core elements. So we have our Disaster Science to Action portfolio. So that's basically taking unique NASA research and basically putting it into action to help communities and develop novel ways of using Earth science and Earth observation data to help communities around the world get a better understanding of disasters and how they might impact communities. We also have our disaster response coordination system. So this element of the program actually just officially launched today. So me and Robert were at NASA headquarters today to help with that launch. The administrator was out giving remarks, and our whole team. We have been supporting disaster response for many years, but this new element of our program is going to give us even more resources and capabilities to help the partners we work with around the world. And then we also have our Disasters Partnership and Learning Initiative. So that's basically how we develop resources to make our science more accessible for communities around the world and build relationships, because it's really important. NASA produces a ton of different science and data, but getting it that last mile to actually be able to help the decision makers and actually impact communities and get it into forms and formats that people around the world can actually use takes a lot of work and a lot of community building. So we're really all about forming those communities and bringing that capacity to those different communities. So I'll talk about each of these elements, and I'll start with the Science to Action portfolio. So as I said, this is part of NASA's new Earth Science to Action strategy. So NASA this year is taking a really renewed focus on getting science and data into the hands of decision makers and communities and making that data more accessible. And to do this, we have a portfolio of projects. So what you're seeing here is our actual previous project portfolio. We're in the process right now of selecting new projects to fund for the next 2 years. But these are the ones that we funded for the last couple years. And you can see they span the gamut of all different types of disasters across the entire world. Oil spills, fires, floods, volcanoes, you name it. And what's really unique about each of these projects is that they all partnered with a different community or organization to get that science directly in the hands of end users and actually helping people on the ground. So really having a extreme focus on being useful to end users and communities. And so I'm not going to cover all these in detail, but I picked out just a couple that use GPM data in their research and in their work, since this is a GPM 10-year anniversary seminar. So the first one is a global flood early warning model developed by Dr. Margaret Glasgow. So this is something called model of models, where they basically combine multiple hydrological models with near real-time satellite data, and that's where iMerge near real-time half-hourly precipitation estimates come in. And they can actually get estimates of global flood risk and severity several times a day for the entire globe. And this is one of the first times that there has been a flood severity model that covers the entire globe. And so they actually partnered with an organization called the Pacific Disaster Center. And the Pacific Disaster Center has a global hazard awareness platform that many organizations around the world use for hazard monitoring and disaster monitoring. So they integrated this NASA model of models, unique flood model, into their platform, and now made it accessible to hundreds of organizations and thousands of people around the world to make this NASA flood modeling technology, powered by GPM in part, available to communities around the world. And I won't spend too much on this one because this is Robert's project in collaboration with Dahlia Kirschbaum. But yeah, this is using iMerge and other topographic data and machine learning to assess landslide hazard risk around the world and generate maps and information about where landslides may be occurring, and giving communities the information they need to take advanced action if there's high landslide risk in their area. And this also partnered with the Pacific Disaster Center. So NASA's Lassa landslide model is now integrated also in PDC Disaster Aware. And if anyone's interested, you can go to the Pacific Disaster Center website, and they have a free and openly available version. So you can actually try out these models yourself and see where there's flood and landslide hazard around the world. And then one final project that uses GPM data is the Hailstorm Climatology Project by Christopher Bedka. And so people may not realize this, but hailstorms are actually one of the most expensive and devastating hazards around the world. in the US causing around 10 billion in damages yearly. And so to mitigate the impacts of these, the insurance industry worked with NASA to develop hailstorm climatology models to basically determine where around the world there is most likely to be hailstorm damage, and that can help them better provide payouts and protection for people around the world that are affected by hailstorms. And so GPM microwave imager data was actually used to develop and also trim data from the previous mission to GPM was used to generate this climatology that gave the insurers the information about where hailstorms are most likely to occur around the world. So now I'll move into our disaster response coordination system, the new thing that we're all very excited about, bringing this earth science data into the hands of decision makers to actually help when disasters are happening. And so, yeah, what it really is about is working with partners around the world. So NASA is not an operational agency, but we work with operational agencies like FEMA and NOAA and different local government agencies. We work with organizations all over the world, non-governmental organizations, private sector stakeholders, and basically anyone who could benefit from Earth observation data. We try to forge partnerships with them and determine what their needs are and adapt our data to fit those needs and to help them when disasters are happening. And so basically, yeah, empowering communities with data. And yeah, we do a lot of work during what we call blue sky periods. So basically working with these organizations when there's not a disaster happening so that we can better support them and leap into action more quickly when a disaster strikes, which is often unexpected. So yeah, I couldn't help but adding just a couple photos from our launch event, which took place today. We had the NASA Administrator, Senator Bill Nelson, came out to give some really inspiring remarks on NASA's role in disaster response. NASA Earth Science Director Karen St. Germain on the lower left there, and then our program manager Shana McLean in the upper right, and the disaster response coordination system manager Josh Barnes in the lower right there. And then in the center, you'll see we invited some of our key partners that the disasters program has worked with over the years, senior representatives from NOAA, FEMA, USGS, NIST, and USAID all came to our event and participated in a roundtable discussion where we talked about how Earth science and data can help benefit organizations during disaster response. So the disaster response coordination system is a whole of NASA effort. So it's actually very unique. It's one of the first organizations that works across multiple NASA centers, and we basically work to pull the best available science and data from these 6 different NASA centers. And so we have what we call response center coordinators that help gather the data from those centers, and then subject matter experts across those centers. And so when a disaster happens, we pull these different representatives across centers to get data that could help the partners that we're working with. And yes, this sort of goes on about what I said. And so here's some actual examples of how we've helped with different disasters over the years. So Hurricane Ian in 2022 was one of the most devastating disasters in Florida history. In particular, the storm surge really caused devastating damage across the Florida region. And many people don't realize this. People associate hurricanes typically with heavy winds. And while the heavy winds are damaging, storm surge and flooding is actually statistically and historically the most devastating and damaging part of hurricanes. So we supported FEMA, who's a very frequent partner of ours. We work very closely with FEMA, and as they are, the operational disaster response agency primarily for the United States. So we worked very closely with them and helped fill in some gaps in their data. They have, aerial flood monitoring capabilities, but we are able to fill in some of those gaps with satellite data. And we developed some new novel products to support that response as well. We also worked with an organization called the World Central Kitchen, who's another frequent partner of ours. And basically, we're able to give them maps and data to help them understand which areas are most impacted and most in need of aid. And the World Central Kitchen sets up mobile kitchens and food stations to bring relief and food and water to people that are impacted by disasters. This was another huge disaster and one that we participated in heavily. The earthquakes that struck Turkey and Syria in 2023, extremely powerful, caused many casualties and widespread devastation, sadly. It was a all hands on deck effort for U.S. agencies, and we were happy to be able to provide help and support with that. We shared damage maps, so we're actually able to identify where buildings and structures may likely be damaged by looking at before and after satellite data, synthetic aperture radar data. We were also able to map landslides and help responders on the ground determine where they could send aid based on those landslide maps, and also worked with USGS, the United States Geological Survey, to help them better understand the faults and geological conditions that led to the earthquakes. And then another disaster we supported was the Tonga volcanic eruption and tsunami in 2022. So it was one of the most powerful volcanic eruptions in recorded history. It sent ash and gas high into the stratosphere. There's still aerosols from that eruption, I think, to this day in the upper atmosphere. And it sent tsunami waves literally across the entire world. But the local island of Tonga were most heavily impacted by those tsunamis. And so you'll see in the bottom right, those are some of our damage proxy maps that show some of the damage to structures and communities on that island. We also helped with SO2 emission data, so to track the volcanic gas plume. And many people don't realize that volcanic ash and gas has a really negative impact on aircraft that are flying through the air and end up rerouting, causing aircraft to be rerouted so it doesn't damage them. And it can also, volcanic ash and gas also causes severe air quality concerns and health impacts from that. So the third component of our program is the Disasters Partnership and Learning Initiative. And a major component of this is the Disasters Mapping Portal. So this is our free and openly available geographic information systems portal, where we put our science and data into formats that different response teams around the world can more easily use. And so that's one of our primary ways of getting data into the hands of end users. And you can explore that data yourself at maps.disasters.nasa.gov. And so, yeah, these are some of the examples of how our portal has, enabled and supported different disaster responses around the world. To date, the disasters program has helped with over 300 responses around the world in the last decade. So we've been very busy, and we, with the new disaster response coordination system, I think we will have the capacity to be even more helpful and help more organizations and communities moving forward. And so, as I mentioned, community building is a really big part of our mission. And so we go to different conferences. These are some photos from the ESRI GIS, Federal GIS conference and the user conference. And so it's really important to work directly with end users and different partners around the world to understand their needs and figure out how we can better get earth science into their hands. And story maps are one tool for that, for building understanding of how to use Earth data and understanding of the various products we provide and how they can be used to support disaster response. So yeah, we really encourage you to reach out and connect with our program. If you are part of an organization that actually does disaster management or disaster response, you can reach out to the DRCS at this email and let us know about the types of things you need that would help your community. I also encourage you to sign up for our disasters community newsletter. So if this kind of thing interests you, how earth science data can help disaster response, then get in touch with us through our newsletter, and you can see the latest news and information and resources that we have available to support disaster response around the world. So yeah, thanks very much, and yeah, happy to answer any questions in the chat.
Well, thank you so much. I mean, the fact that we have so many people who joined us this evening from all over the world and are just wondering, what is going on with extreme weather? What's going on with the impact of climate change on extreme weather? What are some specific ways in which we can see this occurring, as in with the landslides? And how are we responding to this as a world community? So I hope everyone goes away kind of feeling maybe a little empowered, by having this information, by getting a sense of the fact that we've got all these really, really bright, capable, dedicated, caring people from all over the world who are helping us better understand and respond to these issues. And yeah, we've got a lot of wicked problems ahead of us. And we've also got this incredible, incredible group of dedicated professionals who are using information from space and from the ground, and then reaching out. In the 13 years that I've been with Goddard, it has been nothing short of amazing to see the ways in which we interact with and work with FEMA and NOAA and all of the different organizations, not just within the United States, but all over the world, to respond. And a huge thing right now is really, how do we adapt and how do we mitigate these problems? We're not gonna make landslides go away, but what can we do to help people understand that when you're building on a slope and you've got a lot more buildings there, and we've got greater precipitation that's occurring in these storms in this particular area, say particularly during an El Nino season, obviously, there are ways in which we can be working together with the government and with local agencies and with architects, to be able to help people understand where they want to build and how to build sustainably, and the various factors that they need to take into account. So let's go forth, all of these amazing people. I know all my wonderful Texas Master Naturalists, all my Globe friends, solar system ambassadors, people from all different walks of the world that are joining us here today. Go away, share this information, learn more by digging into that resource packet. If you have some resources that I left out of that packet, reach out to me. I am totally accessible. I will put my my email in this in the chat. And the nice thing about using this format that I use is that I can always add more links to the same link. I can add more to that same website and continue to build it. So whatever is useful, we're all in this together. So we can do this. We got this. And thank you so much. Thank you, Jacob. Thank you, Andrey. I know you've had a really, really busy day. Being down at headquarters today, being there for the launch of the disasters portal. You rock. You so rock. Dr. Emberson, Dr. Adler, Andrea, I'm sorry. You're always there for us. Ebony as well. Just thanks to this huge, amazing support team that we have. We so value having all of you join us, and we really, really value the opportunity to be able to share with you some of the cool things that we know about, and then be open to this networking and be open to learning more. With that being said, the next webinar we're going to have on July 11th is going to be focusing on remote sensing. So what is this remote sensing? How can we measure information related to landslides and hurricanes and flooding and drought? How can we do all this with these satellite assets? What is remote sensing all about? What does it tell us? What are the limitations? What are the advantages? We have a really, really nice group of speakers that are going to be presenting lots of different perspectives on remote sensing and what it can tell us, sometimes what the limitations are of what it can tell us, and more. So thank you everybody for joining us. I will stay on for a little bit in case there's anyone who has any more questions.